Welcome to the lecture video of color models. Now, what do we mean by color models? Let's first look at that. The purpose of our color model is basically in computers or in digital systems, we try to create a 3D coordinate system, which is also called a color system, where in that 3D coordinate system, every point there represents one single color. And this is how we have created, till today's date, multiple color models which cater to different demands of different technicalities or different softwares that we use in computer graphics today. So before jumping on into different color models, let's first discuss what do we mean by achromatic or monochrome colors. If we look at the example here, the color ranges we see here starts from black and ends at white. Now, the intensity of black ultimately decreases onto a white color at the end. And how can we achieve such monochrome colors? The word monochrome basically stands for black and white, or at times it provides us with different intensities of gray color, which we can see here in this example. And how can we achieve this? Monochrome colors take place, or we can achieve them, when the three components RGB are of the same amount. So suppose we have an RGB component of 0, 0, 0. This color basically will represent the color black. Now from here, if we keep increasing them with the same amount, as in the next color that we may achieve is 0.1, 0.1, and again 0.1. So this color may take us to this a bit lighter black color, which can be called as a darker gray. So varying the intensity of RGBs, but making sure that the amount of R, G, and B are of the same percentage, we get monochrome colors. And we can see that from monochrome colors, we basically can never achieve pure colors, or colors that we may see in real life with our eyes and which we want in our digital screens here, right? We cannot simply enjoy graphics when they are represented in monochrome colors. Hence, monochrome colors cannot show us realism in computer graphics due to their inability to show us pure color. As in, we do not see any full or bright colors. There is simply no intensity or saturation or brightness, as we just basically see dull colors from black to white. So after this, we basically move on to additive color. Now, what do we mean by additive color? So this terminology basically means that if we take red, green, and blue colors, red, blue, and green colors, and we mix them in higher intensities, if you look at this middle zone here, which is this region where red, blue, and green are at their maximum amount, we get the brightest color, which is white. So in additive color models, when we keep mixing more and more colors, the color itself keeps getting white. It starts from a dark color and ends at a very white color when we have the three of this color at their maximum percentage. This sort of model represents additive color models. An RGB color model applies the additive model. In our digital system, additive color models are implemented here. And as I just mentioned that RGB color model applies this, let's have a look at the RGB model. So here we see a color cube which has the 3D representation here. Now in this color cube, this is basically a 3D Cartesian coordinate system. And in this 3D coordinate system, as I have mentioned during the topic of color systems, every single coordinate, that is, every single coordinate in this color cube or 3D coordinate system, every point is basically a different color. So let's study what is going on in this color cube. Since in the RGB model, we have three components, red, green, and blue. They have assigned them in the three axes here. So the z-axis is red, the x-axis here is green, and the y-axis here is blue. And if we take a look here, if we have a point right on the green axis here, there is no coordinate for blue or red axis here. And this is the maximum green can be. As in, we have the typical numbers ranging from 0 to 255 for red, 0 to 255 for green, 0 to 255 for blue. But in this color system, we have scaled it down to a range of 0 to 1 for every component. And hence you can see that the maximum value red, green, and blue can be is 1. Hence, going back to our previous discussion, that is, if I have a point which lies only on the green axis, we have green value as set as 1, but there is no red or blue component. Hence, the coordinate of this point is 0, 1, 0. Similarly, if we have a point right here on the red axis, we do not have any coordinate for blue or green on the red axis. Hence, the coordinate of this point is 1, 0, 0. Similarly, if we take a point and place it only on the blue axis, it does not have any red or green points, only the blue maximum point. So the coordinate here is 0, 0, 1, as in R and G, they are both 0, and the blue is maximum, 1. So since these points lie on the axes themselves, how about I place a point here which is, suppose, equidistant from green and blue here, but it still does not have any red component. What can be the possible coordinate of this point? If we see this has an equal amount of green and an equal amount of blue here. Hence, the coordinate of this point is basically 0, 1, 1. And when we have a color which has 0 red component but equal blue and green component, if we look at this right image, we get the color cyan. In this region, this color cyan has equal blue and green in it, but no amount of red. Similarly, if we take this point here, which has an equal amount of green and an equal amount of red, but no blue component, we get the color yellow of this coordinate point. And if we see this point here, we see that equal amount of green and red gives us the color yellow. Next, if we take this 3D point here, which has an equal amount of blue and an equal amount of red here, but no amount of green. This color is basically magenta that we see here. Equal amount of blue and red, but no amount of green present here. So this color cube is perfectly represented using this 3D coordinate system. And every point here or every coordinate here represents any one color from this color cube. So this is how the RGB model is basically represented using a color system. And if I remove these points and show you another part, which is, suppose if I have a point which lies directly on the origin of this coordinate system, at the origin, basically we have coordinates 0, 0, 0, which is given here. And if RGB components, all of them are 0, 0, 0, we basically get the color black, which is stated here. And however, this point could not be showed in this color cube here, since the back side of this color cube has not been shown here, as in the part which is represented here and which connects to this part here, the corner of the other side of this color cube will basically show us the black part, as in this part here. This is a CMY model, which basically has the reverse color cube. We will discuss that a bit later, but just in order to show you that if I rotate this 360 degree, we basically get the backside of the color cube. And here, this point has RGB value of 000 and shows us black. Now, moving on to our previous discussion, which was the point at the origin gives us the color black here. And if I have a point here, a 3D point here, this point gives me the value 111. RGB, 3 of them have the value 1 here. And if I get 111 as the RGB color, this basically shows me white, which is this portion here. If we look at this corner of our color cube, this part has the color white. And this coordinate is actually the one that we have drawn here. And if I connect a line from the point black, as in from the origin to this 3D point here, and I connect them using a line, any point or any coordinate that lies on this line will be providing me with these monochrome colors, as the line will give me coordinate values where the R will be equal to G will be equal to B. All these three will always give me the same value, but with varying amounts. And if I follow that line, the colors that I will be seeing will be monochrome colors. So this was all from our RGB model. If we look down here, there are a few pointers that you can learn here, or you can take them as notes from the RGB model. Next, let's move on to our subtractive color model. We have just studied about what additive color model does, which was if we keep mixing more and more colors, the final result will keep giving me a more brighter or whiter color. But in our subtractive color, this is actually the reverse. If I keep mixing colors, the final amount will try to give me the darkest or the blackest color that's possible here. This color model is basically called a subtractive model. If I keep mixing more and more colors, the end result will give me a darker or a black color at the end. And where can we see an example of this? In real life. In real life, if we keep mixing colors, whenever we are painting, if we keep mixing more and more colors, it suddenly turns a very dark brown or a very dark gray, and ultimately a very black color or a muddy black color, hence showing us how the subtractive color method works. Similarly, the CMY model, which I have previously hinted a bit while showing the color cube here, the CMY model follows this subtractive model. How so? If we again try to create a 3D coordinate system using our CMY model, we see that this model is basically the reverse of our RGB model. Why so? How do we get CMY? C stands for cyan, and this is actually an equal mixture of green and blue. How do we get magenta? Magenta is basically an equal amount of red and blue. And how do we get yellow? The color yellow is basically an equal mixture of green and red. This has no blue, this has no green, and this has no red. So the CMY model is basically the reverse of our RGB model. If we represent the magenta, yellow, and cyan in the three axes, we see that if I place a point here, the amount of cyan would be 1, but magenta and yellow are 0, 0 here. Similarly, if I place a point here, the amount of yellow would be 1, but cyan and magenta would be 0, 0. If I place a point here, the amount of magenta would be 1, but cyan or amount of yellow is basically 0. And if I place a point right at the origin, in the origin, I have CMY value as 0, 0, 0. And if I place a point on this 3D part, which is basically here, suppose if this was my color cube, and I place a point here, this point, this black point, is basically where my CMY, or this point where CMY will give me a value of 1, 1, 1. And again, if I join a point from this part to this part, any point on this line will again provide me with the monochrome colors again. And hence, we can actually connect the CMY model with our RGB model. How so? The CMY model is basically just the reverse of the RGB model. If we can see here, in order to find C from RGB, C's formula is basically just 1 minus R value. And why is that? We have recently learned that cyan is just a mixture of green and blue in equal amounts. And hence, in order to find how much of the color cyan is present here, we need to subtract it from basically how much red is there. The amount of red that will be missing, the amount of pure cyan color we will be seeing. And hence, in order to find cyan, the formula is just simply 1 minus R. In order to find magenta, since magenta has no green in it, so the formula will stand as 1 minus G. Because the amount of less green there is, the amount of more magenta there will be. Similarly, for yellow, since there is no blue in yellow, it will be just 1 minus blue in it. So the amount of blue there is, the amount of less yellow there will be present. And similarly, suppose if I give you a value where my RGB is 0, 0, 0, that would mean that the value for CMY will basically be, if I plug in these values here, and since these are all zeros, CMY will stand as 1 minus 0. So this would be 1. So do we see that when 0, 0 means the color black for RGB, right? But when RGB is black, CMY should be also giving me the color black, right? Hence, we see that CMY gives me the color black when it is 1, 1, 1. So the black color is here at the front of this color cube. And RGB model gives me the black at the back of them, right? Which we cannot obviously see here. It's at the back of that color cube. So this is how we see that the CMY model can be easily converted to the RGB model and vice versa, simply using this formula here. And where can we use the CMY model? Since the CMY model basically generates darker and darker color whenever we mix more and more colors, it is ideal that we use them in color printers or copiers where it's necessary that we see darker colors for a better legible result. Let's see an example of another example of how can we convert RGB to CMY conversion or vice versa. We are given an RGB value of 64, 128, and 192. Mind you that the value given here is not a scaled value, as in the range here varies from 0 to 255. So we need to scale it down first. So the R component is divided by 255, so are the green and the blue component. Now we have the scaled values, and using these scaled values, we can calculate and find the CMY values. How so? we will just simply follow the formula which I've just discussed above. C is 1 minus R, so 1 minus whatever we have found here. This is the result of C. 1 minus G for magenta, so whatever we have found here, we have plugged it in here. This is the final CMY result, the magenta result. And for Y, this is 1 minus blue. So whatever we have found here, we have substituted that value here. So we get this answer. So CMY values would be 0.749, 0.498, and 0.247. Mind you that we can actually go the other way as well. Suppose if this was the question given to us and we were asked to convert the CMY to RGB, all we had to do was R would have been 1 minus C, so 1 minus whatever value we have here, so 0.749. If we were asked to find the green one, not the blue one first, the green one, it would have been 1 minus M, magenta, which is this value here. So 0.498, whatever we find here, and the blue would have been 1 minus yellow, so 1 minus whatever we have here. So 0.247, that would have been our answer. And if at the end of our answer we are asked to scale it back to the 255 zone, we would have had to multiply with 255 these answers, whatever we find here. And that would have been our final answer. So that is all from RGB to CMY conversion, vice versa. And before moving on to our next topic, the last thing that I would like to discuss regarding CMY is that if we look at the result here of maximum amount of yellow, cyan, and magenta, we should have gotten a pure black color, right? Because that's the darkest color out of all colors. But if we look closely here, this is actually not black at all, and rather a muddy or a very dark brown color, which basically means that we are not able to get the color pure black from the CMY model. And hence, in order to get this true black color, in the CMY model, we have added another parameter, the K parameter, which basically acts on whenever we want to see the color pure black. So in our computer systems, whenever we want to generate the color pure black, and if we are using the CMY model, we set another parameter, K, and set its value to 1 whenever we want to see the color black. So using the help of this K parameter, we can finally see the true black color in the CMYK model. And hence, now we can get hold of all the colors that we want in our computer graphics.